My name is Mohammed Al-Audi. I'm a lecturer in data science in University of Stirling, also a member of Stirling Vision and Image Processing Group. Today talk we will talk about the reflection symmetry detection in 2D images, because it can be expanded more to be in 3D. So this is our agenda. We'll try to give an introduction and we explain what's symmetry, and after that we define what problems that we try to solve, what kind of related work that we have so far, and what kind of framework that we presented. We have a lot of points, but I think we'll try to cover the first one, and based on the time. After that, we can keep the rest available if someone to see the rest. Okay, so what's the symmetry? So if we look here in these two images, the first image is from Westminster Abbey and the second one from Toronto University. We can see that it's about repetitive object around some point. For example, if we see this column, we see that we have some kind of repetition of details around the column. If you look in the window itself, or if we go to what we call outdoor environment, we can see here the tower is really splitting the image into equal details in the sides. Symmetry is not something new. It's already presented in all civilization, for example, in Chinese or the Egyptian civilization. We can see that in very fine details, for example, in the statues or in a painting, we always keep we try to keep identical details in the both sides. If we try to split this object in two halves, or this painting in two halves, or even when you look in the large environment, for example, we can see here in terms of a temple or a house, we always try to keep details in symmetry. And symmetry actually started to be used mainly in last century or last decade. It started to be used in computer vision application. For example, if we look here in the medical image compression, these are like MRI brain and of a brain object, and they use it. For example, if we cut the brain in two halves, this scan in two halves, we can see that the details can be easily very repetitive. That's why what you try to do is they keep one half and they keep the difference between one of the halves to the other. So this only the change that you can see different from the, if we take the mirror of this half against the other one. So now they can do some kind of compression and reduce the file size for this kind of scan. Or it can be used for example, in the depth estimation. If we can look in this kind of image, we can look in the scene and it's mirror over the water. From that we can define the horizontal line. From the horizontal line, it can help us to do the vanishing point estimation. Also, when we talk about symmetries, there is two ways we can talk about globally, like if we try to make all the regions are contributing to this kind of symmetry, or we can look at locally. For example, if we look in the face, we can find a lot of symmetry on the arms, we can find a symmetry, or in the legs, for example. There is very different types of symmetry. We have the reflection, which we are focused on, which is called sometimes bilateral or mirror. And we can consider as a single symmetry, which we have one object and we try to find a single symmetry, or two or more objects, we call it multiple symmetry. Also, the other types are like, for example, the rotations, means that we have repetition of patterns across one point or around one point, or translations that which is like freeze or whatever. For example, you can see it in the facade of any building. We can see that it's really repetitive, and we can create some kind of mesh grid over it. Or the medial axis, which is like kind of representation as we can call skeletonized any shape. So if you have any shape, you can skeletonize. And this case is very similar to reflection, but the only difference that it can be curvy symmetry, we can say somehow. In our case, what we try to focus on is that we try to look in the major symmetries. For example, if we have this image here or this image here, we're trying to look in the green ones, not in the red ones, because the red ones is just contributing only the minor details into one symmetry. For example, if we look in this symmetry here, it just means only this object are contributing this one, or this one is contributing only this object and this object, but not all the image. For example, this one is contributing all the details into it, or the horizontal one is contributing these details to these details by looking in the mirror. So when we look in the related work, we can see that symmetry detection is not something new. It starts from the 80s. start from the 80s by looking in the intensity, by looking pixel by pixel, and try to find where the symmetry inside the image. And after that, starting in the early 90s, they start to look in some features inside the image, and after that, trying to do some kind of calculation to figure out how it can contribute these features to get the symmetry inside the image, or some key points we can say. And this is where that's where the baseline algorithms are falling inside. So it's Loy in 2006 and SecuNet in 2014. Afterwards, also in the same time, actually in the 90s, the people start to consider it as a segmentation. So they start to, rather than think about feature points, they start to look in objects. For example, the faces inside the image, and we try to say, okay, if you have face here and face here and face here, we try to use the faces or this object as starting to find where the symmetry inside the image. And of course, in the last 10 years, we can find that a lot of people using learning-based algorithms. And by using, for example, start with SVM, after that, the supervised neural networks. And we can see that the recent work is from Funk in 2018, and it gives a very, very promising result, but needs a lot of training data. Oops, okay. So if we look in here in the baseline, the first baseline, we can see that they take a safety points. So what they do is extract safety features. After that, they try to do matching by looking in every safety feature and the inverse of the other points, or the inverse of the descriptor of the other points. And based on that, they try to project all this matching into a polar-based voting system. And from the voting system, they find where is the peak point and find where is the symmetry inside the image. And here's some example from the publication that is published in 2006. The issue of this methods that they are very, very sensitive to the SEFT feature extraction, which is, for example, the scale, and it doesn't take into consideration for it the age information. As we see here, the SEFT, he found only these points. This one, he tried to focus only that he found symmetry here, or only because he has a very, very few points that he already found that the symmetry is just 1 point. That's why in 2014, SecuNet, he came with another day, say, okay, rather than looking in the SEFT, we can look in multi-age age extraction by using wavelets. And he tried to find where is each segment inside the image. After that, he do similar triangulation as we did in the previous one. And he also project that into a polar-based voting system and find where is the symmetry inside the image. And here is a result we can say. So this is a result of a voting space as this one. And here is a result that we get based on the voting space. So this red point is representing this symmetric axis somehow. And we can see the difference between the white line and the blue line, that he trying to do a convex. He just tried to find where the symmetry exactly inside the image, rather than just looking in the inline segment, by looking in which points are contributing to this symmetry, and doing a convex hull computation. Okay, just to find the endpoints of this line. But this issue, of course, we have a lot of when you look in the age information, you have a lot. If your background is really too much information, it can affect your results, and you start to have a lot of noise in the background and affecting your result where you find this computation, as you can see here, or you can see here and here. Plus, he don't use the texture information. The recent algorithm in Funk, he considered it another way. He say, okay, let's look in one of the very famous solving for computer vision by deep learning, by looking at the image and trying to find where we can segment the object from inside the image. And he say, okay, let's do the same. Like if we have an image here and we're trying to find where is the symmetry object in it, and we try to consider that when we look in the red or the voting, we consider only the parts which are representing the symmetry axis and where it's contributing to it. And how he does that, he just do a transfer learning, and he try to take a semantic segmentation method or model, and he try to add some layers, and after that use these layers and try to do a training by doing just transfer learning training and freezing some layers in the beginning, and he gets the result somehow. But the issue is that based on what he learned, what he can get as a result. So that means if you don't learn different, or if he has a new environment, he will not learn how to predict the symmetry in it. For example, if we can see this object here, and he trying to find, based on what he learns, that if we can find a symmetry here and a symmetry here, a symmetry inside this biggle and this biggle, but because he don't learn to find symmetry between objects, that's why he can't find the symmetry between this biggle and this biggle. For example, as the same here, he can find inner symmetries inside the object, but he can't find symmetry between the object itself. So he lack the geometry learning to find the major symmetry inside the image. So these all the points, and we try to look here what is what is the drawbacks of every category what we have. We'll focus only in the feature one, which is really the feature-based symmetry, which are looking, which has some issues to find between, or to there's confusion between to find what is the local and global symmetry inside the image. But it's very, very promising, and a lot of people publishing in this direction. Plus, of course, the learning-based one. Sorry, this should be learning. How is it compute, or how is they do evaluation metrics for that? So they usually use a true positive way. So if you have ground truth and you have a symmetry candidate, so what you do, you go to the centroids and try to calculate the Euclidean distance between them. So this is the first criteria. The second criteria, if you take the same ground truth and just project it near to the symmetry candidate and calculate the angle between them, this is the second criteria. And based on these two criteria, they try to find if it's less than some kind of threshold, it's considered as a positive. So we have gamma threshold, and we have zeta threshold here. And based on that, he can calculate the position on call and maximum F1 score. So what is kind of threshold? So what happens in this kind of symmetry detection? There is computation happens. So there is computation from CV4R in 2011, 13, 2017, and every time they try to change how this threshold is computed. So first one for the angle threshold, they use 10%, 10 degrees, and it reduces somewhere some part in the stage of the computations. It reduces to 3 degrees. Regarding the distance, they say it should be 20%. If the threshold should be 20% of the length of the ground truth, or 20% of the minimum of the length of the symmetry candidate or the ground truth. And sometimes they already change it in some cases that to make it 2.5% of the minimum width or height of the image itself. What kind of data sets that we have so far? We have actually 3 data sets. We have the Pennsylvania data set, which is released in 2011, 2013, which has for single symmetry, we have 157 images. And for multiple, we have 142 images, which include inside multiple symmetries around 580 images. And also Seconet in 2016, he released another data set from New York, which he take it around New York. And he would use these kind of images for symmetries. And in the last competition in ICCV in 2017, they released 100 images for single and 100 images for multiple, which it has around 384 symmetry inside. And here are some examples what kind of images that we have. So in Pennsylvania one, we have images which is like synthetic image like this one, and this one, and this one. We have indoor images or focus on some objects, for example, these ones. And we have images which outdoor, for example, the frog here or a tree here somehow. And we can see from these kind of images that the images are really low resolution images, because in this kind of stage, I think 2011, we don't have really high resolution, or we don't have capability to use some kind of hardware to give high resolution images. And in New York, as we see before, we have some images from in New York itself. So we can see that he go around and he tried to look in some images around New York and try to find where is build the ground truth based on these images. In ICSV is the same images as Pennsylvania, but they adding more images. They include more images, similar way, synthetic, indoor and outdoor. One of my contributions that I try to build a data set which is high resolution images based on the demand that we have now in the domain, because now we have a lot of mobile phones that it can take a very high resolution image. Plus, it has what we can say photographic sense somehow. So these images are more quite difficult to find because it has some kind of perspective view. For example, as we see here, as a perspective view, or for this one here, or very, very challenging because, for example, if you look here, this image that the details are not appearing. We have a solid scene, we can say. So what kind of frameworks that we try to propose? That we try to propose that if we give an input image, we try to extract. So if we look in the framework, we have input image, we get a feature extraction, so we get the feature points. From the feature points, we do a feature triangulation, so we can get some kind of symmetrical weights. And from symmetrical weights, we build a symmetry representation. So that's what she gave us at the end, the voting space, where we will look where is the symmetry, where is the peaks, so we can find where is the symmetry axis on for it. So for the, I think in this talk, we'll talk only in the feature extraction, and we'll not focus maybe on also weight if we can have some time. So Loy, as we said before, he talked about SIFT. Sequenet, he's looking only in Gabor wavelets. So what we consider here, we look in log Gabor wavelets in this case. And the symmetry weights, we say that Loy, he using the texture-based feature descriptor, and Sequenet, he using the edge information of the Gabor wavelet. In our case, we'll use the edge, the texture, plus the color information together. Okay, I think we'll ignore the other ones, the representation and selection, because we don't have time for this talk. So if we look here, what we can do? So if we have an image, we apply some kind of bank of wavelets, and we get points, feature points, and these feature points we have X and Y. And based on X and Y, we can do a triangulation. If we have, for example, I and J, we do a triangulation with according to some kind of origin to the image. What's the origin? It can be the middle of the image, or it can be the top left or the top left corner of the image. And based on this triangulation, we can define rho and theta and the weights, the symmetry weights that we need to contribute for it. And we can take this kind of triangulations, set of points or a set of candidates, and we can build it based on a representation, which it can be H, which can be built out of voting space for us. Based on that, we can do, based on the voting space, we can apply some kind of maximum suppression, and we get where is the symmetry candidate inside this kind of image. Here are some results that if we can input image, we can get multi-scale. After that, we do multiple orientation. After that, we can get amplitude map and orientation map from that. And from the orientation and amplitude map, we try to build some kind of, to find in every cell. So we do it like a cell based. And every cell, we try to find where is the maximum amplitude and maximum orientation or corresponding orientation. And based on that, we can build some kind of histogram based on the wavelet response. So if we have an input image based on multi-scale and different orientation, we can get here some kind of result. If we try to terminate the very, very low values, we can get what kind of points as we can get as a feature points based on this input image with different, which point came from which scale. And based on triangulation, so if we have 2 points, we can build how to get the rho and theta. It's easy. So if we can build a line between the 2 points, and after that, we try to take in the middle way, we can take a perpendicular line. So that's why, if we consider this as the origin of the image, is the center. So if we build a projection from this point to this line, it represents the rho. And if we take this line and we try to project it near to the center here, which is connected the 2 lines as a perpendicular, and we calculate the theta, this is theta. So how we get the weights? The weight is so easy. I think we just take 3 weights we take into consideration. We're taking the magnitude of every wavelet response plus the difference of the angle, and the second one is the histogram calculation. It's a histogram based calculation. It's a summation of minimum intersection of histograms according to each point that we take in consideration. For example, this point and this point. And the last one is similar. Is a minimum intersection of histogram, but rather than looking in texture, we look in color. In this case. So if we consider here, if we look in the result, we have Loy using SIFT and Sequenet using Gabor. In our result, we try to show results contribution 1 by 1 and see how the result we can get. The same for weights. Here we use texture, here we use edge. We try to use edge and texture, or use edge and texture and color at the same time. And we can see here some kind of result, what we can see. So if we have some kind of ground truth in a multiple cases here or multiple symmetries, we can see that our results is represented here. These are Loy results. And these are our results based on every our contributions that we can get. And we can see that our results is getting better by looking in to find a symmetry inside every object here. Okay, I think I have 1 minute, so I will go for the quantitative results. Also here we have the different data sets, the single symmetry and the multiple symmetry. And we can see the result of Loy and the result of Sequenet according to the true positive from the evaluation matrix of 2013. And we should see every contribution, how it look like. The red ones is the top, the highest score. The second high score is blue. The third high score is green. Okay, I think I'll skip the rest of the things and we'll go for the summary. So what we try to show here in our representation, we're trying to show that we have a global, a reliable global symmetry detection to get the result of it. And we're trying to focus how to use the Gabor to get a better global access to plus by using the texture and the color information for that. I don't talk about this point, but we already provide also a ground truth for single symmetry inside artistic images or professional images by using AVA dataset, which is a larger dataset that built before all that.